Hi there. So I'd like to talk about this paper, like a kind of like so-called graph filter paper. It's a pretty recent paper last year, and I guess before getting into the paper, I need to talk a little bit about the title is like Advances in Distributed Graph Filters, by these authors here, and I guess I need to kind of have a quick quick review or explanation of the graph filter. So the idea there is we're trying to do kind of like signal processing on graph. So think of like if I'm doing like signal processing in maybe in 1D or 2D, maybe in 2D or on an image, then basically you can think of like on each pixel there I have some signal, right? So maybe this is an image, and on each of the pixel I have some values here, and then I process these signals. Maybe I have a filter and so on and so forth. Now we want to try to, of course, this is a 2D. This 2D for image. We can also play with 1D, maybe like audio signals, 1D, just one dimension there, or maybe we can have like 3D, like maybe a sound. Think of video stream that like for each time frame we have an image, so we have like kind of like three-dimensional data like that. So we want to extend this idea to arbitrary structure topology. So then then that comes with this graph signal processing or graph filter idea. So you can think of like, for example, like in images, like each of the pixel here, so you can think of a node of a graph. So then essentially this image is like a signal on a kind of grid graph, or like a rectangular on a grid or something like that. And on each of these node here, we have some signal. Signal will be simply a value assigned to like each of the node there. And then we can do filtering. For example, the filtering would be in the sense, okay, I'm trying to pass signals, for example, like from nodes, like from here maybe to here, and somehow this node here will affect like the node here. So, but of course, like it's much more convenient if we kind of do not let our procedure kind of like constrained by the topology of the graph. So that comes with this like distributed graph filter idea. I guess the name distributed is a little bit misleading in this sense. So it's more like we want the filter to be done not in a centralized manner. It's not completely misleading, but then it's really, I guess a better word for that is like some local filter really. So I will have the signal here. We only when I filter the signal, let's say I start with some signal here. I just arbitrarily put some number 1, 2, 3, 4, 5, 6, 7, 8, something like that. So let's say this is the filter values here, and when I process this node here, of course when I do a filter, I need to take into some filter in the sense it's just I want to modify the value of the signal at this point, given the signal at this point, and in other points or like in other nodes, other signals on other nodes of on the graph. And when we say local filter, the dependency of we try to modify these signals will only depends on the signal on the current node and also the signal in the neighboring node. For example, this 7 here will only depends on so for this node here, if I will try to, in the next time instance, I compute a new value for these guys, will only depends on this one, this one, this one, and this one. So And actually, this is very much related to the graph network. So that's in the old network, there's the graph network idea that is basically like I would say it's very similar, but here, like in classic graph cell processing, we are interested more in a more restricted sense, only in a linear filter. Set there's no nonlinearity here. So therefore, like for example, this node here, maybe for the next time instances, I trying to have like weighted sum with this labeling signal by some weight, let's say, and that's the main idea here. And then let's say now if I try to represent this guy, so let me introduce some notation to be more specific, like what's going on. So I have the graph here will be specified by a set of the node, the vertices, a vertex set or the node set here, and the edge set here. So basically, for simplicity, I will have the vertex here will be, for example, like if I have, maybe I just give a very simple graph here, maybe like this, just a simple like 5 node graphs. I have like A, B, C, D, E here. So then my vertex set will contain A, B, C, D, E, something like that. And my edge set will be, so if I assuming I just undirected graph here, so will be like containing the pair of the nodes here, so that for each of the edge. So for example, like this is an edge, so I would have like AB is an edge, and maybe if it is okay here I'm undirected, I will just make it a pair as this is like an order pair. So AB, this when I have AB, I also have BA, something like that. But if I have a directed graph somehow, I may want to specify that AB is different from BA or something like that. So but in here, like I just assume that it's undirected here, so I have AB and then like BC and then like maybe BD and DE here. That's the edge sets here. And then so then to specify like this graph structure, is typical to use this kind of like adjacency matrix there. There's like A. The adjacency matrix is basically I have a matrix that of size the n by n, where n is the number of nodes there, and with like A, B, C, D, E here, A, B, C, D, E here. I guess I put I have A, B, E, D, okay, A, B, C, D, E here. And then like when I have a connection there, for example, A, B have a connection, I just put 1 there. If I have here like, and also AB have, if it's an undirected graph, AB have a connection, BA has a connection as well. It's basically this matrix will be symmetric. And then BC will have an edge here, something like that. So I have a 1 there. BD have a 1 there also, and also DE has a 1 there. And of course, this is symmetric, so I have something like that. Now for graph filter, so with this, when I want to represent a graph filter, what I have is like I will have a signal. For example, on this graph, I start with a signal. Let's say like the original value is XA, XB, XC, and so on. And I can form a vector of that. Now I can have for each of the node there, like as I mentioned, if this is a local filter, in the next value, so basically I want to make a linear filter, I want to have this is like the current value of the current signal values at each of the node there, and after multiplying a matrix, I get the value of the nodes after the filtering. And as I said, like because I want to make the filter local, so the signal only depends on like the current node itself, and also its adjacent neighbors. So what it means is that like, I can put in some number here, for example, like 1, 2 here, but I cannot put number here. You see, because like A here does not connect to C here, so there's no direct connection to the C here. So these places are forced to have 0. And for the second row here, again for the because you look at maybe I repeat again. So for the XA here, this is the old value. I have the new value here. If I look at like this first row position here, this one is like what this one is relating to like these guys here, right? So therefore, like for this several coefficients here, I have to be 0. Otherwise, XA will be relating to like XC, XD, and XC, to the previous XC, XD, and XC, and that's not allowed because it's not directly connected. Similarly, in the second row, like XB is not connected to XE, so therefore, like I have to be this 0 here, and the rest I can have some value, I don't know, I don't care. And then like here, XC here is connecting only to B, so except for like B and itself, all the places have to be 0. So as you see, like therefore, like this filter, if local, if and only if that like I think of like A here, I want to make sure besides the diagonal, everywhere like A is 0 in that matrix, I mean the elements is 0 in the matrix A, I have to be 0 in the filter as well. So let me just say that this is a filter. Let me denote this as like F for the moment. This is an F matrix. And that's a more elegant or like mathematical way to write it is that we can define the support of a matrix, support A, as like the index in the matrix, or the location in the matrix that A is non-zero. So, and in that sense, it means that like this filter is local. Let me find some space here. Maybe I write here. F is local if and only if like A plus I, the support of that. I mean, okay, F ij is non-zero only for ij. Fij is non-zero, ij in the support of A plus I. So I A plus I because I only allow the diagonal to be non-zero as well. I don't mind that to be non-zero. And that's the distributed graph filter we are referring here. Distributed, why we say distributed is in the sense why we want to have local is like we probably don't care about like the local property if like we have the filter implement in a centralized manner. If like the entire graph signal is in one centralized mainframe, there's no reason we need to make it this complicated. But on the other hand, like if we think of like the application of all this is like trying to maybe do some like social network study with the you have like users like directly doing some filter in their own mobile phone or something like that, and they have constructed a very large graph, and the user only see the labels. That's basically the friends there, and then in that sense, like you should only have a set of signals from your friends or so on, right? So therefore, like in that case, you expect that the filter is supposed to be local. So therefore, like these two things is kind of equivalent really when we say you're considering a local filter, it's the same as the distributed filter. Okay. Before I continue to talk about the content of the paper, maybe I have just give a quick review for like Fourier transform and like extension to like this graph signal processing. So as you know, like Fourier transform is like it doesn't matter. It's like a discrete Fourier transform on a discrete domain or a continuous domain. I mean discrete time or continuous time domain. Basically, the Fourier transform is like you have a signal. Oops. Let's see. You basically have a signal. Maybe I have some signal here. I don't know how to have some whatever signal here. And what the Fourier transform does is essentially trying to kind of project this signal into different sinusoidal signal. Basically, we are going to do given a sinusoidal signal of different frequency, and then I come to do a kind of inner product of this signal with this signal. Then with that, I will get the power for that particular frequency, and then I have another frequency signal. Maybe this is a frequency f1, this is a frequency f2, then this one will maybe f1 this when I say frequency f1, maybe this is a the signal itself, let's see, this signal itself is f, let's say, and then this is like what is that, let me just call it G1 for the moment, and then this is G2. So this is G1 with frequency f1. Oh, that's pretty bad. Maybe this signal is H. So frequency f1, and this is like frequency f2, and so on. This is like the frequency f1 meaning that like maybe if this is a continuous signal, then like G1 is a minus I. Let's see, f1 2 pi f1. Let's see, to x, something like that. Like you have this. Maybe I make a t here, ft g1t here. It's a sinusoidal signal like that, and then I change the frequency here, and then like I have different sinusoidal signal, and I think that may be fine. Oh, yeah, I think that may be fine. Okay, I may have conceptually it's correct. I may have some put some. Yeah, I think it should be fine. So anyway, and then I have G2 is something like that, like 2 pi. Actually, it's better to just have like no minus here, something like that. And this is a HT, let's say. And then you think of that my Fourier transform, like my Fourier transform, this H here. So let's say this gives me a Fourier transform is H, or maybe some people use notation H hat. Maybe I still use a notation of big H here. That is like the frequency of the Fourier transform of this signal here. So this will be like have taking argument is like the frequency. I say this a frequency f1 that will be just equal to the inner product of ht and this g1t here. And if this is complex domain, the inner product would be like something like ht like g ei to pi f1t, and take the integral like for the entire domain dt, something like that. So and for the and what the theory of this kind of like they call it this spectrum theory, I guess. Is that like you can decompose this signal into like as long as your kind of like this signal is like band limited or something like, then I can like represent this signal with frequency like within this band basically. So with like Fourier transform of with like Fourier transform component of this within this frequency band. Okay, it makes lots of sense, right? If my HT is band limited in the sense that it can get up to frequency up to this like maybe big W here, then as long as I know the frequency components, basically all this HF HF for F is like within like minus W to W, then I'm going to be able to recover this HT here. And yeah, that's okay. That's the high level idea here. And what we have here, you see, is like basically we have the signal we projected into this sinusoidal component. When we recover that, okay, of course one thing that is important why this like components here can recover this is because like this bases here, like I call it bases here, like G1, G2 and so on, they do not do not interfere with each other, in the sense that like if I think of like these have different frequencies here, in general I will have like this frequency 2 pi f 1t e I 2 pi f2t. This will be equal to 0 when f1 is not equal to f2, or basically the inner product of these two signals, like when they have different frequency, when you try to compute the inner product between these signals, they will give you zeros. And then like the Fourier transform, therefore like it's essentially another way to looking at that is like you have a number of let me just put it in you have a complete basis function, and in this case it turns out that just sinusoidal function are the basis function. And what we're going to do the Fourier transform is just we have an incoming signal like h here, we are projecting h onto each of these bases here to compute like how this h kind of like correlated with like each of these bases here, and then that essentially the Fourier transform coefficient will be basically the power for that particular frequency or for that particular basis, and we recover that will be simply to when we get this Fourier coefficient, we will be just like recover the original signal as weighted sum of like all these basis function weighted by the Fourier coefficients. Okay, let me just put it more clearly. So let's say I have f1, f2 here, and so on. Let's say if I have a discrete domain, I have fn. Let's say this is n basis here, and this kind of actually it doesn't need to be discrete, but what means, let's say the complete basis turns out to be, let's just have a discrete number of these basis signals here, and then like I'm going to have like Fourier transform, let's say f h as I said, fh is equal to maybe big H here, and hfi is equal to, oh, actually I called it G earlier, I think I called it G earlier on the previous one. It's just equal to the inner product, right? H with Gi here. This is the frequency, and this is just the signal there. I get the inner product, and then like when I recover the Fourier transform, and I see why people like to put just H hat there. So maybe I just use H hat here. It looks a little bit more precise, I guess. Maybe I put H hat I is equal to, I have H here in the product with this G, and that gives me just the projection, basically H onto Gi here, and that is the Fourier coefficient. And here I just denote as Hi here. That's basically the Fourier transform. This is these are the Fourier transform, right? And then I can recover the original signal H, then will be just equal to my H here projected by Gi, sum over I, let's say that. You see that it makes sense because like this, what I have here, I will have it actually I will have this is equal to H Gi in the products times Gi here, right? Something like that. And then if you can verify that this makes sense, because if I do it in the product on both hand side with like some Gj here, let's say, and then I will have like equal to I H Gi and Gi Gj here, and this is basically delta function Ij, because like these bases here are orthogonal to one another. Okay, I'm looking for that word. Yeah, they should be orthogonal to one another. So the inner product will be just equal to 0 when you pick like G1 and G2. And I will assume them to be normalized as well, like G1 inner product with itself is just equal to 1. So therefore like this will give me just a delta function, delta Ij. So therefore like this here is just HGJ. So as expected. So that check that like indeed like I will have this inequality here. I mean, we will have this equality here. So this is an abstract way to kind of like interpret like Fourier transform, and so now if we think of like we extend that like to graph signal processing, then one property that we have is like we think of like when do we get these bases here? Why do we have this sinusoidal basis here to begin with? So we have this sinusoidal basis because this sinusoidal basis are shift invariant. So in the sense that if I have a shift operation, you think of a shift operation here. If I shift this guy here, so if I have this, if I have any of this Gi here, and let's say I have a shift operator, I shift this horizontally. I have maybe I just denote with S. I shift this guy here. So what I get is still a sinusoidal signal. So it's still a sinusoidal signal, but probably multiplied by a phase factor here. For example, like I shifted by if I shifted by t, then probably I have like ei ft, something like that, somewhere here. So but you see like if I look at this as a linear operation here, so if I model this shift operator, I mean the entire thing, if I just vectorize that, so this operator become somehow a matrix, and this signal here, just let's say a finite vector. So assuming that here I'm drawing a continuously, but if I discretize that, it becomes a vector. Let's say it's okay, I just use GI here. And then like this, I have this thing is just multiplied by number, maybe lambda, then I GI here. Then what you see is like I have this GI here is actually the eigenvector of this shift operator, or like shift matrix operator here. And that holds like for, so therefore like what we have is really, if I have a shift matrix operator, these sinusoidal bases are all the eigenvectors really. And so therefore the Fourier transform is nothing but it's a if is that like we are projecting the signal into bases of a shift operator, shift operators eigenvectors, or bases constructed by the eigenvectors of the shift of a shift operator. Now, in terms of graph, this is a little bit tricky. So if we have like 1D signal, maybe we have a train here or a path here, we have a shift operation. Like for example, like I have a one node here. Next time I move to this one. Next time move to this. Next time move to this. Then I have a essentially like a shift, right? But if I have a kind of like more general tree or even graph, if I think of like this thing here, next time move to this here, next time move to this here, it doesn't in general like a shift operation, but we will just generalize this idea anyway. What I mean is that like we think of like a ordinary 1D signal as just a kind of like path graph here, and you can think of a discretized 1D signal, discrete time 1D signal as just a path graph here, and then the shift operation when I shift by one unit here is, for example, like let me just give a concrete example here. So if I have a concrete example, let's say I have 5 nodes here, so I just call it 1, 2, 3, 4, 5, let's say. And then if I shift it in the sense like first it starts from here and then it moves to here, then my operation, let's say if I start with a signal like that, next time instant I should have 0, 1, 0, 0, 0, right? So therefore like for me to get from here to here, what I have, I should have something like this way. So I need to have like 0 here, and then for this one here I should have 1 here, right? I should have 1 here, and I'll actually more maybe I just put a more precisely, let's say if I have like x1, x2, x3, x4, x5 is the original signal here. Now if I shift that, like have a shift operation, it become like my x1 move to this second location, so therefore like I have x1 here, and I have x2 move to the third location. I have this x2 here, and x3 here, x4 here, and let's say like my x5 actually going to move back up here, and then I have x5 here. Then for this case here, for me to have like from this to this here is just a permutation matrix. I should have something like x1. I think I have something like that, and then like 0, 1, 0, 0, 0, and 0, 0, 1, 0, 0, and 0, 0, 0, 1, 0, right? Something like that. And if this is for the directed case, so now let's say like I have an undirected graph, like we kind of like, I would say generalize this idea, but in the sense it's a little bit sloppy way, but that's how people did it, like in graph signal processing. So they're thinking, okay, let's have this is like a adjacency matrix for a directed graph, right? So something like if I shift this, so of course in this case actually I should put a 0 here. Actually this make more sense. Okay, this is like the adjacency matrix. What I have here is like the adjacency matrix of a directed graph like this, right? So it's like I have each time, actually I do not make this arrow correctly. My arrow should be the other way around. So each time my signal at the first location move to the second location, and the signal from second location to third location, and third location move to fourth location, so on and so forth. So and that's precisely will give me the case if we look at the Fourier transform. I mean, if we try to decompose this matrix here, of course I will have some boundary condition here, but if my path is infinitely long, then I should just get back sinusoidal like eigenvectors for this matrix here. Now, but people like don't always study like directed graph. Actually, most of the time people study undirected graph. So therefore, like what happened is like let's just extend this to undirected graph laterally, even though like it may not make sense. So in that case, we'll still use this adjacency matrix, because this is actually the adjacency matrix for this directed graph, right? So let's say if I have not even a directed graph, if I have like just this graph now, and then I will still like take this again. Maybe let me repeat again. So in this case, when we in the classic Fourier transform case, we just argue that like the sinusoidal bases are actually just eigenvectors of the shift operation there. So the shift operation like this, and the shift operation in terms of graph in the 1D case, in particularly for the directed graph, it's just the adjacency matrix. So therefore, like, okay, let's say like we'll just extend this, and we in this case, like this is adjacency matrix, we'll just say like say something known as a shift matrix. We just assign shift matrix as an adjacency matrix in general, even though it's not a directed graph, and it's not a path graph, it's not even a directed graph. We'll just assume that we can do that. So then for example, if I have something like that, my adjacency matrix for an undirected graph, I will have very similar to this, but will be symmetric. So I should have like 1, 1, 1, 1 here, and 1, 1, 1, 1 here as well. And I will basically take this again as the shift matrix here, and I will try to find the eigenvector. So I assume that I am able to decompose that. So if I decompose that, it's like u lambda u. I always have problem the way I should put the let's see. Yeah, I think it's right. I should no, I think it's not right. I think I probably should, yeah, put put the transpose here. So then U is actually the eigenvector. I mean U is a U1 and UN here. Let's say these are the eigenvectors of S. Because actually if you look at this here, what I have is if I multiply U on both sides, on the left hand side, and here U here is okay, maybe I should specify U is unitary or like orthogonal. You can think of everything is real, it's orthogonal, and this is the diagonal matrix, it's just have the eigenvalues, and U transpose here because it's orthogonal, so then U transpose is equal to identity here. So therefore it means that I have SU is equal to lambda U lambda, something like that. So then if I put it as a U1 up to UN here, it's like U1 up to UN lambda. Then if I look at like each of the columns, for example, like this multiply these guys like SU1, SU2, and so on, SUN, right, for each of the columns, and will be equal to like, this is a diagonal matrix, lambda 1 up to lambda n will be equal to lambda 1 U1 up to lambda n UN for each of the columns on the left hand side. So therefore like I have basically SUI is equal to lambda IUI. So it's like this is an eigenvector. So so that's actually just a quick review for eigenvector, eigenvalue, and some linear algebra. So then I decompose that way. I decompose this S now. So in general, again, it doesn't necessary this is a diagonal directed graph or not. More often, I will assume this is undirected graph, and then I will just take the adjacency matrix as my shift, and then I will just decompose that, and then I will get the eigenvectors, right? So now the Fourier transform in this case will be, I'm going to do a projection to this Fourier to this basis here, right? So therefore, like if I have signal like my signal, let's say like this vector is just x here, I call it vector x. Then I basically have a Fourier transform. Is like I have x going to do a projection to each of the bases. So I have like x m u I, so to get the I coefficient of the Fourier transform, or I can just write it in a matrix form. So this is will be like U transpose, let's see, yeah, times x. So U transpose, because it's a U1 transpose up to U n transpose, right, times x. This will be like the inner product for that. And okay, this I cannot write it equal here, but this is the I component is equal to that. So I'm just saying the Fourier transform, the Fourier transform will be just a U transpose times x, something like that. And then like the I component, so therefore like the this is the I component. I component will be just a x and UI times x transpose, or UI transpose times x. And then when we try to do the inverse Fourier transform, then it's like very natural. We just multiply by U again, right? So U transpose times x, and then times U again, I will just get the inverse transform. Now then then when I want to do a kind of like a filter, for example, like in the sense that you think of like low pass of high pass filter, the basis here, of course U here, U1 up to UN, they can have like basis of different frequency. For example, like if you just again look at the classical case here, I may have some bases with like a lower frequency and some bases with higher frequency, and then like I can, like for example, like for the projection of the signal, or the signal projected to this high frequency signal, I can just uh, give it the, just maybe set it to 0. Like I have a low pass filter, I will set it to 0, or like say a small value, and when projected to the signal, I mean the Fourier basis that with like low frequency, I will just keep it there, then I will get a low pass filter. So then in general, like I can have like maybe I have this is like Fourier transform, like Fourier, and then inverse, like this is Fourier transform, inverse Fourier transform. So I can have like Fourier transform, then multiply by D. This is a diagonal matrix, and then multiply by U again. That can do something like classic low pass, high pass type or band pass type filtering. But of course, in this case, there's no proof here like how this like Fourier basis supposed to look like. Because as I said, like if this is a directed graph, we know that it's a sinusoidal, something like that. And but if I have like for example undirected graph, or even like a tree, or like well, I should, okay, here again, if it's a directed path, it's not even a graph. If a directed path, then it's a sinusoidal, the Fourier basis sinusoidal signals. But if I have it's a undirected graph, and also like undirected, not a undirected path, even like I can have like trees, or I can have loop, that can be a general graph here, then it's not very clear when we kind of decompose this S here into the eigenvectors, what this eigenvector is supposed to look like. But anyway, that's what people did. So that's basically the concept here for extending like Fourier transform from classic signal processing to graph signal processing. I guess maybe okay. I guess I spent quite a lot of time here that I didn't even get into the paper that's completely reviewing the materials. So maybe I will talk about that in the next video here. Maybe a final remark here is that like my I have this shift matrix here, as I mentioned earlier, and this shift matrix does not necessary to be assigned as this adjacency matrix. People also use, like for example, the Laplacian matrix. The Laplacian matrix is something like A minus D, something like, where D is like the okay, this is a repeated notation. I'm sorry about that. But the D here is like the how do they call it? Basically, it's it counts the number of connection for each of the node, basically. So for example, like for this graph here, let's say don't have this here, then the D here will be like, I will have this one, I have one neighbor, so I will have D equal to 1. So it's a diagonal matrix, so the rest will be 0, but the diagonal value will be just equal to the number of neighbors of that node. So for this guy here will be 2, and then this one is 2 again, and this is 2 again, and this is 1. So I have D is equal to that, and I will have the Laplacian matrix is equal to A minus D. So yeah, I forgot A minus D or D minus A. I think it's A minus D. If I make a mistake, I will make a correction in my in my description there. So therefore, like it would be like something like that. Right. And or you can have something known as the law, the unsigned unsigned Laplacian. I think this is unsigned Laplacian will be like a plus d, so then I will have something different. And then there's also normalized Laplacian. So there are different like graph matrices like people study, and like theoretically, or you can all use that like to as the shift matrix. Even though honestly the rationale is not clear for A. You may say that okay, it kind of like emulate the classic Fourier transform, at least if you consider the graph is actually a path. Also, like if you consider the directed case, then indeed the shift operation is really just the A. But as we extend to other cases, it's quite weird why we see like L and so on. Even though like there's some maybe I won't say more now, but maybe like when times come I can say more. But I think this kind of things like people are not certain yet, so they I guess it's as far as we determine the shift, and then we just kind of create this basis because I have this set as I determined, and my U here, let's say is I form a complete basis, then at least what I can claim is that like if this is a complete basis here, all the signal can be represented by this basis here. So at least this Fourier transform, what I'm saying, like this transform is like invertible. But of course, like this transform may not have like as obvious or meaningful like physical interpretation than in the classical case, because like in the classical case you always get this sinusoidal path here, but here like you get some weird Fourier basis signals, and then when you projected that, you say this is the Fourier coefficient, then you play with that, and then kind of convert it back like Fourier inverse Fourier transform. But anyway, like having said that, like I think most of the time if you pick A and L, especially the L, like people do observe that like you will have like bases that have like high frequency and lower frequencies. So therefore, like at least you can just like do a certain extent like some low pass filter, for example. This is like how people use it. Like in a typical case, it's like you really have a graph signal there, then you do the this projection like into this Fourier basis, and for the high frequency component you just like reduce that, reduce the coefficient, or like you just cleared it out completely, and then you do the inverse Fourier transform. Then essentially you have a low pass kind of like low pass filter to your graph signal. So maybe you have some, this can do in a certain extent I do a little bit denoising on the graph signals there, or maybe you can we can even kind of like fill in some missing coefficients. For example, like if I have parts of it I don't know what is that, then maybe what I can do is I just set it to 0 or something like that. Then hopefully I will fill back this value here when I so anyway, okay, I guess I'll just stop here. Maybe I will really come back to talk a bit more about that paper next time.